right, well, shall we? It's Halloween. Nobody dressed up?
I'm my dad.
You're your dad? Is that is that what that is? Okay. I had a student in my Cal 2 class that dressed up every day.
Like a big
Every day he was dressed as a bear, like a Winnie the Pooh. You may have seen him on campus.
Yeah.
Yeah.
Doesn't wear shoes.
Doesn't wear shoes, yeah. So I was curious to see if he would dress up today as not Winnie the Pooh. Yeah. I don't know. Okay, so we kind of informally started chapter 4 last class, and now we want to formally go through this. So we are starting with 4.1, and the title of the section is Maximum and Minimum Values. So there's going to be a lot of definitions here, and I don't expect for you to sit here and copy all this down, because this is all in the notes that's provided online. We're just going to talk through them and then look at some graphs, and I think once you look at the graphs, you'll have a pretty good understanding of what these definitions mean. So the first definition here says, if we're given a curve f, okay, so we're given a function, we define that function on some domain, which we're going to call capital D, and there's some number c inside that domain, then f of c, that's the function's value at that point, will be called the absolute maximum value of the function on D if f of c is greater than or equal to f of x for all x in D. That's just fun to read, isn't it? All this is saying is that you've got some curve. If you can find a point inside that domain or inside that interval where the point on the graph is higher than every other point on the graph, then you have located the absolute maximum value of the function. And then the other way would be to talk about the absolute minimum value of a function, which means that that would be the lowest point on the graph. All right? In either case, if you have a maximum or minimum, in both cases these are called either the global maximum or minimum, or sometimes they're called the extreme values of the function. So these are all words you'll start hearing now. Oh, look, we found the global max. Oh, look, we found the extreme value, right? We're talking about highest and lowest points on the graphs. So that's the definition of an absolute maximum. Then we go and we start talking about something called the local maximum. So it's pretty much the same definition. It's the highest point and the lowest point. We call it the local max and local min, but there's one exception. This point does not have to be the highest point on the entire graph. It just has to be the highest point locally. And I'll explain that when we look at pictures. And then this says local min means you're the lowest point not on the whole graph, but just locally you're the lowest point. Now there is one more thing here, and I'll get back to this, but this is added to the notes. This is not in your notes. I added this today actually. And I'll express this when I get to the visual examples. So here's our first example. We have a function, right? And if we were to start here at the left side, start moving along this function, right? We go up and then down and then back up. And because I have dots here at the end, what I'm saying to you is that the function starts here and stops here. So this function is actually defined on a closed interval right now. Now, when we talk about the absolute maximum and absolute minimum, we're looking for the highest and lowest points on the graphs. So here are your global extreme values, your global maximum, your absolute maximum. This point right here, that's your global minimum, lowest point on the whole graph, right? Now, in terms of local, the local extreme values or the local max and mins are those points. Let me take the globals out. The local max and mins are here, 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 and the endpoints. That's what I need to add to this. Endpoints of a function, as long as you're on a closed interval, the endpoints are always local maximums or minimums. So let's talk about why this is a local minimum. Is this the lowest point on the graph in this little local neighborhood? It is, right? Is this the highest point on the graph in this little local neighborhood? Yeah, so it's a local max. This one is not a global max, right? It's not the lowest point on the whole graph, but locally, it's the lowest, right? Okay? Yes?
So like you couldn't make that argument like if you had like a straight line
Uh-huh.
and you picked the point at the top. You couldn't be like
Straight line with a tilt or
the top. Like say you just took this midsection, like going from this to like say you took that.
as a separate graph? Or
Yeah.
Okay, so like if you had a function, let me get my markers here. You want me to do closed interval like this? Okay,
So on that, the two endpoints would be the maximum and the minimum, both global
this would be global max,
and global.
global min, but these would also be locals. This would be a local min and a local max.
But so what I'm asking is like, if it's just in this, so when you say neighborhood, are you referring to just like that little area, or are you referring? Because
Yeah, so you should have trouble with the idea of local, because local is subjective.
Because I was gonna say you can put the dot in the middle of the like that mid part right there and call
Ex-
that local.
Yeah, exactly. So local is one of those words. Do you remember when we were doing limits? And I said there's a precise definition for a limit. It involves this delta epsilon thing that I'm not going to get into in this class. But I think we did the analogy of me like saying, are we close to one another? Are we close to SeaWorld? Are we close to the sun? Do you remember me talking like that? When you say local, you have the same exact sort of thing happening. Does local mean like zoom in, zoom in, zoom in, zoom in? Or does local mean like that? So for us in here, local is going to mean visually somewhere in here. We're not going to try and complicate it. You could create a function that starts to cause all sorts of problems with that definition, which means that mathematicians actually have a better definition that's more precise that we won't get into.
So would it have to be a peak then? Because all of these are peaks or valleys, right? So if you had a local maximum, right, and you were being super like anal about the local part of it, and you chose like the straight line segment, kind of, yeah, like
Like
say
this?
you chose that.
Uh-huh.
Could you call like a point in the middle of that a maximum?
You
'Cause it's
couldn't.
not a peak,
Okay,
but
yeah,
it's a
I see what
local.
you're saying. Okay, so like
zoom in on that scale.
if I picked, let me make it a little curved. Like if I picked that point right there,
Yeah.
could I consider that to be a local max?
Yeah.
And the answer would be no. And the reason why is because if I zoom in, even if I zoom in, a billion times, I'm still going to have the point. I'm going to have to the right of it, it's going to go up, and to the left of it, it's going down.
Okay. So it has to be a
So
peak or a valley.
has to be a little peak or valley within the function when I zoom in. No, good questions. So pretty much understand this? Local max, local min, and global min. Local max and global max. Local min, that's it. Local max. All right? Not loco, local. Okay, how about this one? This graph almost looks like the same one, but it's slightly different. Okay, so I'm going to point to the points and you tell me what they are, okay? Local max? Nothing, okay? Global min and local min. Local max. Local min. Local max, global max.
The endpoint's always going to be.
Endpoints are always locals, but not necessarily globals. In this particular example, the endpoint over there is a global max, and then this point right here is our global min. In both of the examples I've given us, the pictures we're looking at, the functions are on closed intervals, aren't they? Closed. So here's the next one. Now I need to add something to this picture. I want to put little arrows here. And the arrows indicate that the function goes up forever in that direction, okay? So this function is not on a closed interval now, right? This function is actually defined on the entire number line. All right, so if I put my finger here, that point right there, it's nothing, right? Because it continues to go up, so that can't be a local max. Come down, nothing, nothing, nothing. We get here, global min and local min, right? Local max, local min, and then there's nothing else, right? So here we have a we have a global minimum, right? But we do not have a global maximum. We have a local maximum, but no global maximum. There is no highest point to this function because it just continues to go up. All right, does that make sense? So these are our locals, and that's our global min, and there's no global max. Okay, how about this one here? Local max and global max, right? Local min and global min. Local max, local min, and global min. So when we talk about the actual global min, global minimum, we're talking about the Y value that comes out. So this this global maximum has a value of like 200 something. I think I have it labeled. Okay, so the value of this is 225. So the global maximum is 225. Now it happens in two different places, doesn't it? But the global maximum is still the same. If this side of the graph went up just a little bit higher, then we would only have a global max at one place. But here, it's happening at two different places. And the global minimum is actually happening at two different places also, right? So make sure you understand that when we're talking about these things, we're talking about the Y values, right? Not the X coordinates. And then our locals, we had this, right? Those are our locals. All right, so now we get to a theorem, right? And before I start this theorem, I want to just illustrate something, big picture here. Right? In this section, or in this next 3 sections that we're going to do, we're basically going to be trying to tackle 2 different types of problems. Is that a question? Yes.
So just before we leave it,
Is there, if you had a graph like that was like if you had like x cubed, then and it was you had 2 endpoints on each, then with the left endpoint, would it be a minimum?
Yes, both local and global.
Okay.
Right?
where there's no point.
Pardon?
Where there's no point, we just go down.
It just kept going down, so I put an arrow here instead. You would have no global minimum. You'd have no global minimum. Now, if I stop it here, then I have a global max. But if I continue it, this would be an example of a function that has no global minimum, no global maximum, and no local anythings, right? Do y'all see that? Just goes up, flattens out, comes up. There's no place where you have a peak or a valley.
So if that was x cubed and there was only one endpoint, then that point would be all of it? All
Wait.
the local minimum and maximum?
Where, like right here?
If you had a point.
Just make this an endpoint here.
So
That
would
would
be the local minimum, local maximum, and global minimum and global maximum?
No, this would be just your local minimum
Oh, okay.
and global minimum. You can't say it's a maximum, because to say it's a maximum means it needs to be the highest point
Yeah.
on the graph, and this is obviously not the highest.
There's just no global.
Yeah. Okay, does that address that? Okay, so we're going to be trying to tackle 2 fundamental problems, all right? The first fundamental problem is we're given a function on a closed interval. I think I referred to this a little bit, yes? Does this look familiar or no? Closed interval. we want to try and find these highest and lowest points. And then the other one is doing it on an open interval. Okay, where I have a function that might do this, but the ends don't ever stop. So we're interested in finding these points, okay? And in fact, in this one, we want to look at that point and that point also. We're interested in finding these points. The method that we use to do this is much easier than the method that we use to do this, all right? So today is about what we're going to refer to as the closed interval method. And you only use it when you're trying to find highest and lowest points of a function on a closed interval. If that interval happens to open up and it's not closed, then we have a lot more that we're going to have to do, all right? Well, let's get this one out of the way first, and then we move to that one. So the first thing we're going to need in order to tackle this is this theorem. It's called the extreme value theorem. And it says if f is continuous, so you have a continuous function. What does that mean? Continuous means you don't have to pick up your pencil, basically, right? As you draw it, you're nice and smooth and no jumps, no breaks, no gaps, right? If you have a continuous function on a closed interval, then your function must attain both an absolute maximum and an absolute minimum somewhere within the interval. You've got to have a highest point and you've got to have a lowest point if it's continuous on a closed interval. It's impossible to not have both a global and global max and min. That's what the theorem says. Let's try and visually understand why that's true. So here's one example. Let's say I have a function that's defined on a closed interval, right? That means it has a left endpoint, doesn't it? Okay, so here's my left endpoint. And since it's on a closed interval, it's got to stop somewhere, so it's got a right endpoint. If I have to connect those two dots with a function, so it's got to pass a vertical line test, and it's got to be continuous, there is absolutely no way to do it without at some place having a global and a global max and min. So here's the first example. I could connect them kind of like that, right? I mean, that's just an example of a continuous function. And in this case, I will have a global min and a global max, right? See how it kind of came up and came back down? So I have both a global max and min, don't I? Okay, let's try another, just try it a different way, something different. That's a different curve, right? This time, global min, global max, right? Right? Is there any way to do it without getting a global min and max? So I'm sure someone's going to say, well, what about that? Just do a straight line. Global min, global max. Your endpoints are the globals, all right? What about this one? I'm going to try and be clever here. How about I draw this one? I'm going to go like this, but then right here I'm going to have an asymptote, and then off the other side I'm going to connect it. It's not continuous. See, you have to have the continuity. If you take continuity out of the theorem doesn't work. So yes, I could draw an example of a function right here. This function does not have a global maximum, right? Because this thing goes up and it goes up forever. However, it's not continuous, so it doesn't count. So I was trying to cheat, but I can't. Does that make sense? Okay, so let me try something else. Try this one. See what you think about this one. Make this one up myself. Actually, I'm going to make up a few. So take a look at this one. Okay, I'm going to do that one. That one. Okay, I think that's sufficient. These are all continuous functions on closed intervals, right? All I want us to talk about is, well, they all have global max and mins, don't they? They all have a highest point and a lowest point. I want to identify them real quick, but I also want to talk about where they occur. So here, the global minimum is where? Right there, right? This is your global minimum. Where's your global maximum? The right endpoint, right? That's your global min, that's your global max. Where is the global min happening? Somewhere inside the interval, right? Where's the global max happening? At the endpoint, right? Okay, so here we had, one of them was inside, the other one was on the end, yes? Inside the interval, at the end of the interval. Here, global max, global min, right? Where are those happening? Both inside, right? Both inside. How about here? Global max, global min. That one's happening left endpoint and then inside, right? How about this one? Global min, global max. Oh, that's kind of like the first one. Oops, let me get a different one. What am I missing up here? Both endpoints, right? So something like this. That would be an example where it happens at both endpoints. What I'm trying to illustrate with this is no matter how you do it, your global maximums and minimums are occurring somewhere inside or at the endpoints, right? It could be both endpoints, it could be both inside, it could be one endpoint, one inside, or the other endpoint, one inside, right? Do we have to have two? No. Oh, yes, hold on, sorry. We're talking about global. When it comes to global, there's only one global max and one global min. So what about, like, let's take the sine function. God, all my markers are dead. Okay, let's take the sine function, and let's look at the sine function just a couple of periods of this. Right? Like there. Right? There's your sine function. Let's stop it. Let's stop it right there. So we have a global max. Global, 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 right? The global max is 1. Now it happens at a bunch of places, doesn't it? Within the interval, though. And then the global minimums are here. The global minimum is -1, but it happens at a bunch of places. So where they occur, again, is either at the endpoints or somewhere inside. Yes? Okay, there's one picture I've avoided, and nobody has questioned it yet. Does anyone have an idea of a function that might cause an issue? A continuous function? Horizontal line segment. How about that? Here, straight across here. Does that have a global maximum? This one's a little strange, no? What do you mean?
It's a straight line, so you have the goal, it'd be a global max, global min, and max min. You have all the same ideas.
I'm going to make up a value of 4 here. 4 is what? 4 is the what? The global max and min? So what do y'all think? Does that seem reasonable or no?
I mean, if you can have 2 points that are both the global max,
Mm-hmm.
like, why can't you have an entire line?
Yeah, why can't it be every point? So let's go back and look at the definition real quick of global. If you go back to the definition of global, in this definition there's a very important piece to it, and it's that right there underneath that inequality symbol, that little bar, right? That means greater than or equal to. So this means that you're supposed to be a global max, you have to be higher than or equal to every point in the domain. And this means you have to be lower than or equal to every point in the domain. So when you look at this, let me see, get back to the theorem here. No. Okay, that's where we were, right? So when you get back to this, the global maximum is 4, because 4 is bigger than or equal to every other y value in the domain. It's equal the whole time. But it's also the global minimum, because it's It's smaller than or equal to every other value in the domain. So this is a really kind of strange situation where your global maximum and global minimum are the same. And it only happens with horizontal lines. Okay? And not only is it weird because it's both the same, but where they occur is the entire interval. So it takes on that value everywhere in the interval. Okay, moving on. Back to the theorem. So the theorem says that if we've got a continuous function on a closed interval, we must achieve a global max and global min. So our thing would be now, how do we find them, right? If someone just hands us a function, if it's continuous and it's on a closed interval, how do we find those max and mins, right? Global max and mins. So we have a theorem that's going to lead us to that. This is it. This is the beginning of it, all right? We have to be real careful with this theorem. This is called Fermat's theorem. And some of you, I'm sure, have heard of Fermat's last theorem. No, maybe not, but this is not Fermat's last theorem. This is another theorem that Fermat had, all right? So Fermat's theorem says, if f has a local maximum or minimum at some point, and the derivative at that point exists, then the derivative must be 0. All right. So if you have a function that has a local maximum or minimum at a point, and the derivative at that point exists, then the derivative must be 0. Okay. So I'm going to try and visually explain what's going on. I'm going to draw you a picture. Let's say we have a function. We can see a maximum there, right? This theorem says that if you have a function f, if it has a maximum or minimum, doesn't matter, at some point, so this would be, let's do a number line in here. It says if you have a function that has a max or min at some point c, then is it saying that the derivative then must be 0? Is that what this theorem is saying? Is the theorem saying if your function has a maximum or minimum at some point c, then the derivative at that point must be 0? That's not what it says. We have to be real careful. If the derivative exists, then it must be 0. Okay? So in this particular case that I drew up here, we have a local max, right? And the derivative does exist here. Why does it exist here? The way I drew it, right? Where do derivatives not exist? Corners, jumps, right? Cusps. That's where derivatives don't exist. This is nice and smooth. The derivative at c exists. That means the derivative there has to be 0. And you can see that if you take the slope of the tangent line there, it's flat, right? So here's an example that would be in conflict with the theorem that we just looked at. Okay, do you all agree that the tip of this cusp is a local maximum? That's the highest point on the graph, right? Agreed? Now, so that is a maximum. This point right here at C is a maximum. But the theorem doesn't apply here because the derivative doesn't exist. The theorem says if you have a max and the derivative exists, then the derivative must be 0. Okay. So it's a good theorem, but it doesn't handle all the cases, right? So I say here, be careful, this theorem, it does not say that if the derivative is 0, that we're sure to have a max or min. This is a major misunderstanding from students, is that students will say, oh, look, when I draw a function, I look at the max, look, the derivative is 0 there. So anytime I take a function and I take its derivative and set it equal to 0, I'm going to go. That's how I'm going to go find the max and mins, by setting the derivative equal to 0. And I've even said that to you in some way in this class. We're just going to set the derivative equal to 0, right? But that's not enough, because you could also have things like this, where setting the derivative equal to 0 wouldn't help, because it doesn't tell you about what's happening here. Does that make sense? Okay. There's something else in this theorem that I want to talk about before I move on, and this is about logic. I know there aren't a lot of you that are going to do math as a major, but I know there are people that are going to move on to do computer science, and this is a logic thing, all right? So in our logic system, we have these things called if-then statements, which if you've done any computer programming, you know what these are. But if I have a statement like if P, then Q, okay, that's some statement that I could have. In this particular theorem, what we're saying is if your function has a maximum or minimum, right, and the derivative exists at that point, then this is true, right? Does it work the other way around? Can you switch this? Is this equivalent to if Q then P? Like in general, is that true? Is the question. So is this theorem saying that if the derivative is 0, imagine switching the order. If the derivative is 0, then we have a local maximum or minimum. Can we reverse that? And I have an easy way of explaining it to you. Okay? Let's say if you live in Texas, then you live in the United States. Do you all agree with that statement? If you live in Texas, then you live in the United States. Can you just flip those? If you live in the United States, then you live in Texas. No, right? You could be in the United States and not be in Texas. But you can't be in Texas without being in the United States, right? So in general, when it comes to logic and if-then statements, you may not reverse them. And what students get wrong with this theorem is they reverse it. They say, oh, if the derivative is 0, I'm looking at a max or min. No. You can only say, if you're looking at a max or min and the derivative exists there, then the derivative must be 0. So as useful as the theorem is, it doesn't work the way we want it to work. We want it to work the other way, don't we? So it doesn't. Now, how would we know, this is going again into logic, how would we know that an if-then statement works both ways? How would we ever let anyone know that you can go both ways with the theorem? What you'll see is this. You'll see if and only if. So it'll say f has a max, derivative at that point is 0. If if and only if, f prime exists. If and only if f prime c equals 0. So if they wanted you to be able to read this theorem both directions, and it was true in both directions, they would have the first statement, they would have if and only if, and then the second statement. And that if and only if means you can read it that way or that way. All right? We don't have that. One more thing about logic? One more? So if P then Q, let's say that's given, there is something that you can write about this statement that would be true that's backwards, and it's this. Does anyone know what's logically equivalent to this? If P then Q, the equivalent statement? If, we know we can't say if Q then P, right? We just said that's US, Texas, Texas, US.
If Q, then sometimes P?
Well, no.
Doesn't it?
If not Q, then not P. If not Q, then not P. That's logically equivalent. Now let's do the Texas thing. If you're from Texas, then you're a US citizen. Everyone agree with that? Right? So that's true. Okay, a logically equivalent statement to that would be if you're not what? In the US, then you're not in Texas. These are logically equivalent. So anyone who's interested in math later on, you're given a theorem and you're given something and you're asked to show that it's true. To prove it, They say like, if this is true, then this is true. Prove it. And a lot of times it's really hard to prove it. So what you do is you take that theorem and you convert it into its logical equivalent, which is this, and then you go to see if you can prove that. And if you can prove that, then you've proven that. That's called a contrapositive proof. But that's beyond the scope of this class, we're sure. Did you get that from the logic class?
Yeah, I'm in it right now.
You're in logic? Yeah. So truth tables and all that, yeah, okay. You CS major? No?
No, I'm in bio.
Wow, what the heck are you doing logic for? Okay. I guess in biology you have to have some logic.
Well, I took it instead of philosophy.
You did what?
I took it instead of philosophy.
Instead of philosophy? Yeah, I guess it fits in there. I think like all computer science majors, all STEM majors should take a logic course. It's very interesting.
I feel like we literally are doing the contrapositive.
You're doing contrapositive, yeah. Proofs by contradiction, no? Yeah, okay. So, all right, let's get back to this. Okay, so as great as that theorem is, it's not exactly what we'd like, right? So here's some examples of Fermat's theorem. Like I was saying, look, we've got a local max, we got a local min, the derivatives exist, and look, we've got local maxes and mins, don't we? Here's something that fails, boom, there we go. Theorem doesn't apply, right? It is a local max, but derivative doesn't exist. So before we actually get to something useful that's going to allow us to find these things, we have to have a new definition, and it is called the critical number of a function. So if somebody hands you a function f, and they say, hey, look, I want you to tell me what the critical numbers are of that function. We are going to define the critical numbers to be any number that makes the derivative 0 or any number that makes the derivative not exist. It's like there's something happening whenever we have these situations, right? Like when we have a corner or a cusp, the derivative doesn't exist, right? That could be a place we have a max or min. When the derivative is 0, that doesn't guarantee us a max or min either. But it could happen at these two, all right? So these are going to be called critical numbers. And now we get to this theorem, same theorem but kind of revised. It says that if f has a local max or min at a point, then that point is a critical number. So if you have a max or min that's on the function somewhere, then I can tell you something about where it's having that max or min. That's got to be a critical number. Is this saying that wherever we have critical numbers, we have maxes and mins? Is it saying wherever you find a critical number, you will find a max or min? No. It is saying that if you have a max or min, you have to be at a critical number. It is possible to be at a critical number and not be at a max or min. You want to see a visual of that? A visual example of that? We did it earlier. X cubed. It's my crying marker. Right there. Look at that point right there. What's the slope of the tangent line there? Yeah, it's like right here the slope of the tangent line is positive, positive, then it's going to flatten out, right? And just for one instant, it's going to be flat. And it's going to be 0. And then it's going to turn back up. So is that a critical number where this is happening? Is that a critical number? Yes, the derivative is 0 there. Is it a local max or min? No, right? So again, even though the theorem is nice, it doesn't guarantee us where we're going to find local max and mins. So what are we going to do? Well, we're going to just have a very simple method of doing this, okay? This is it. This is the most important thing you need to take away from this. And that is, what is the method we're going to use then, right? If somebody gives us a function on a closed interval, all right? So to find the absolute maximum minimum values of a continuous function on a closed interval, here's what we're going to do. We're first going to just figure out where the critical numbers are, okay? Where are the critical numbers? Or what are they? So where's our derivative 0? Where's our derivative undefined? Then what we're going to do is we're going to take those values and we're going to plug them into the function. And then we're going to take the endpoints of the interval and we're going to plug those into the function. And the biggest number we get out is our max, and the smallest number we get out is our min. Okay? It's a very simple process. we're going to find the critical numbers and we're going to compare them to what's happening at the endpoints. Biggest numbers max, smallest numbers min, all right? Very clean method, and now we get to do some examples. So we'll start out somewhat easy. I want us to find the global max and min of f of x equals x cubed minus 4x squared plus x on the interval 1, 4. Let's make it -1. No, we'll just leave it 1, 4. All right, so in order to do this closed interval method, okay, because we have a function here on a closed interval, right? In order to do the closed interval method, you must first make sure you're looking at a continuous function on a closed interval, right? So we know we're closed, but is it continuous? So how do you know it's continuous? It's a polynomial, and all polynomials are continuous. When we talked about continuity, there was this thing way back then where it said all polynomials are continuous. Okay, so we have a continuous function on the closed interval. So the first thing I'm going to do is I'm going to find the critical numbers. And to do that, I need to do two things. The first thing I need to do is take the derivative of the function and set it equal to 0. That's the first thing I need to do. Then I need to take the derivative of the function and figure out where it's undefined. Because wherever the derivative is undefined is where the derivative doesn't exist. And those are the two things that qualify for critical numbers. All right, let's start with the first one. Take the derivative of that function. We got 3x squared minus 8x plus 1, and we set it equal to 0. Right? That equation is a quadratic equation, so we can either try and factor it, or we can, if we can't factor it, we have to do what? Quadratic formula, right? So I think it's going to be quadratic formula time. So x must be 8 plus or minus the square root of 64 minus 4 times 3 times 1 all over 2 times 3. So that's your quadratic formula being applied to that, right? And what we're going to do is we'll leave it as an exact answer, and then we'll get the decimal answer. Let's get them both. So we'll have 8 plus or minus the square root of, what goes in there? 52. And then over 6. And that's the exact answer. I realize we can clean that up, and we could probably, well, I don't know, we can't really pull anything out of there, can we? Well, can we? 4? Yeah, 4. But who cares? Just leave it. That's exact, right? That's the exact answer. But then we get on our calculator, and we can get 2 answers, right? This is 2 answers, but we can get the decimals for these. Anyone have those? I see people punching away on their calculators. Anyone have my 2.535? Is that what you said? 2.535. And you're rounding there, right? So there's going to be some rounding error here. And then where's the other one? So you want to be sure that on your calculator you can do this. You don't necessarily need to do it right this second, but make sure that come quiz time, you're not like for the first time breaking out your calculator, all right? 0.131? 0.131. All right? All right, so we just found 2 critical numbers, didn't we? Here are the 2 critical numbers. This one and this one. Are we saying that we have a global max or min at these points? No, we're saying we might. Okay? We might. So let's move on to the next step, and then we have to think of something else. Look at the derivative. The derivative is 3x squared minus 8x plus 1. Is this thing ever undefined? No, there's no number you can plug into this that's going to cause a problem, right? This derivative is a polynomial, so it's defined everywhere. You can't There's no square root, so we don't have to worry about negative numbers. There's no fraction, so we don't have to worry about division by 0, right? There's all these things that could happen that aren't going to happen because this is a polynomial. So do we ever have the derivative undefined? No, because this is a polynomial. Does that make sense? Okay. Now, the next thing I'm supposed to do is take the endpoints and plug and take those and do something with those, and then take these and do something with those. But there's a problem. Does anyone see the problem with my critical numbers?
Oh, that one's not in the.
One of those doesn't live here, right? One of those doesn't live in the interval that I'm looking in. I'm only allowed to look between 1 and 4 on this graph. This is saying, hey, look, your critical numbers are going to be here and here. This number's in that interval, this one is not. So what am I going to do with it? Chunk it. Not in the interval, all right? You have to check that. Somebody's going to forget. Don't be that somebody. All right. So now, let me go to the steps. So I find the critical numbers, right? And I evaluate the function at the critical numbers. And then the second step is to evaluate the function at the endpoints of the interval. So I need to continue this step. I need to now evaluate my function. So this is still part of step 1. I want to evaluate my function f at what value? I only have one critical number, right? At x is equal to 2.535. So I want to take 2.535 and plug it into the original function, right? So I'm going to do f of 2.535. We'll have to get our calculator out for that. That's going to be 2.535 cubed minus 4 times 2.535 squared plus 2.535. And that's going to give us some y value. I'll take whoever has it.
6.87.
6.87, is that what you said?
88.
6.88? Negative. Is it negative?
Yes.
Oh, negative 6.88. I saw another shake of a head in agreement. Okay. So when you plug this value into the function, it spits out negative 6.88. We don't have any idea right now if this is the highest or lowest point on the graph. We know that it could be, right? It could be. Could be a highest, could be a lowest. The only other points that could potentially be where we have a global max or min would be at the endpoints. It's either going to happen at a critical number or it's going to happen at the endpoints. So now what we do for step 2 is just take these two endpoints and plug them into the function. So step 2 is I need to find f of 1, and then I need to find f of 4. So f of 1 should be pretty easy. What do we get when we plug 1 in there? Negative 2. So far, this point is actually lower than that point, right? So this is looking like this might be our global min. But we need to still check at 4 to make sure. So what's happening at 4? We get 4 to come out? Okay, we got 4. So that's it. These are the only 3 values we have to look at. We have to compare them. So step 3 now is to compare and come up with a final conclusion. So what would be your global max? Your global max would be 4. The biggest value you see out of these, right? The global max is 4. And it occurs where? Where does it happen? At x is equal to 4, right? When you plug 4 into the function, it spits out 4. So the maximum value is 4. That's your output, right? Your input to get that output is 4 also, just coincidentally. Okay, what about the global min? That's this one, right? Global minimum is negative 6.88. And it occurs where? at x is equal to 2.535. Yeah, so what I prefer on the tests, all right? What I prefer is for you not to write this. I prefer you write it either as an ordered pair or in functional notation. Let me show you what I mean. So I would prefer this, that instead of writing that, you write this. Global maximum, all you have to do is this. Just give me the ordered pair. Input, output, right? Or if you don't like that, you could do f of 4 equals 4. Okay? That tells me the input and output also, right? Here, what would I write? 2.535, that's my input, and the output is negative 6.88. Or you could write f of 2.535 equals negative 6.88. Do you see why I prefer this? I mean, it's less writing in terms of words, but it also just kind of gives me everything I need. Input and output's all there. The only time this would become an issue is if, like that sine function I graphed earlier, where our global max is 1, but it happens like at 20 different places, you wouldn't want to necessarily do that.
Would it be closed?
These aren't intervals. These are ordered pairs. This is an x and a y coordinate, not an interval on a number line. Yeah, that's one of the bad things about our notation in math, is you can't tell the difference between an open interval and an ordered pair. All right, that one was pretty straightforward, I think, because the derivative was easy. And setting the derivative to 0 was relatively easy, right? Because it was a quadratic formula. So if we go back and we think about this a little bit, I'll leave that up there. We've actually now found a way to answer a question that we couldn't answer back in college algebra. We now have a way of doing it. So if I go here, I graph this function x cubed minus 4x squared plus x. And I just look at this on the interval 1 less than or equal to x less than or equal to 4. I'm not doing that right. What am I doing wrong? Something is wrong here. Oh, wait, there we go. Why is that not doing it? I've done this before, so I'm wondering why, what am I? I don't remember. Does anyone remember what it is? No one uses this, huh? One? Maybe a comma. Let me try that. No. No, 1 less than or equal to x less than or equal to 4. I've done it before. That's why I'm getting so frustrated. I don't remember the syntax. No. Well, I can restrict it over here, but that's not the same thing.
You have to make it like y equals function.
I don't think so. I feel like they've almost changed it because I could have sworn it was this. But I'm going to give up. Okay, there it is though. Can you all see that? I'll zoom out a little bit. There we go. So we're only looking between 1 and 4, right? So we're only looking between here to 4, where it stops there. And we did determine that the global max happens at 4 and it spits out 4. And the global min happened at 2 point what? 2.535, which is about right here. In the value, we got that also. Okay? So back in college algebra, we could graph polynomials. We could tell where they hit the x-axis. We could tell where they touch or bounce or things like that off the axis, but we could never tell like how far down they go or up they go. Now we actually have a way of figuring out where those are. It just requires that we set a derivative equal to 0, right? But the good news is that we can do this for any function. So let's try a harder function. Find the global max and min of, let's see, let's throw us into the fire. How about this one? X square root of 16 minus x squared on the interval -1 to 4. All right, first thing, is it a continuous function on that interval? Well, we have to be a little careful here because this is not a continuous function in general. I mean, there are numbers that we could plug in here that would cause problems, like 5. Like if you tried plug in 5, right? Get 5 times 5 squared is 25. 16 minus 25 is a negative number. Square root of negative, we're done, right? Can't do it. So there are some restrictions on the domain of this. But if we look in this interval between -1 and 4, then any number we plug in here for x should be smaller than 16, right? -1, you square it, that's going to be +1. Take any number between that and 4, the worst you're going to get here is that that's 16. And then 16 minus 16 would be 0. Square root of 0 is still 0. So we don't have any domain issues, right? So this should be continuous on that interval. So we can proceed. So what do we need to do first? Take the derivative and then set it equal to 0. So I'm going to need the derivative, right? Let's go ahead and just work on the derivative right now because I'm going to need it. And then I'll do step 1. So to take that derivative, product rule, right? You got to do your product rule. So derivative of the first function, which is just 1, times the second function, plus the derivative of the second function, which is 1 over 2 roots of 16 minus x squared, chain rule, times the derivative of what's in here, -2x, right? But then also finishing off the product rule times x. So times -2x times x, right? And we've finished the derivative. Okay, let's clean it up a little bit. We can clean this up. These 2's will cancel out. And so I get something like this. Square root of 16 minus x squared minus x squared over the square root of 16 minus x squared. And that's my derivative. Agreed? Plus became minus because of that minus x times x squared, put it on top, there we go. That's a pretty clean looking derivative. Would you agree? Now I need to set it equal to 0. So I'm ready to start my work. Step 1 for this process, I need to figure out where the derivative is equal to 0. So to figure out where the derivative is equal to 0, I need to set that equation equal to 0. And I'm going to need to do that over here because I think I'm going to need a little bit of room. So I need to set square root 16 minus x squared